Now, what about discharging capacitor? This is the circuit, as you can see. You go exactly along the same lines. Loop rule, taking into consideration that dq by dt is negative now. Okay, so taking this into consideration when you write this, you get this expression. Again, to have this 0, the as q, when you connect this, q will be decreasing with time here, because when you connect these, this q will be passing from the positive to the negative terminal, and it's neutralizing. So as q drops, I also should drop. Again, construct the differential equation, again for I dq by dt. Arrange things as you can do here. Put the cube part alone on one side and the t time on the other side. Integrate. Now the integration is from q initial to q, because it starts from fully charged capacitor, okay, which has q maximum, and you want to find q at any instant of time. So for any q, and this starts from 0 when the capacitor was fully charged and to any time. Integrate. Again, it's a ln here, okay, between q and capital Q, q initial or q maximum. This q initial is just q maximum. So arrange things, you get this expression. Take its derivative, you get this expression for the current. And as you can see, this goes with what we are talking about. Q here at t equals 0, this quantity is 1, so q is equal q initial, which is q maximum, which is CE. And at t equals infinity, this quantity becomes 0, and so q goes to 0. And this is what happens when you discharge a capacitor. All the charge here will neutralize the positive charge, will all move to the negative charge, and it will get neutralized, and you will have no more charge on the capacitor. For the current, in the same way, at t equals 0, the current is just q over c divided by r. Q over c is what? Is just the potential across the capacitor, fully charged capacitor, divided by the resistor in this case. So as if this is the battery now. But of course, this is moving, this is changing with time. At t equal 0, this is just q initial over rc. And here, as time goes to infinity, this quantity becomes 0, and the current again drops to 0, as we expect. Okay? So the discharging here curve is similar to the charging curve for the current, but for the charge, it is different because it looks like the current. It's exponentially falling again, as you can see from here. It's not exponentially growing now, in the case of, as in the case of charging. In the case of charging, we had the charge, the curve growing exponentially for the charge from 0 to maximum, but here it's dropping. So it looks more than like the curve of the current. If you take the limits as we expect, at t equals 0, the current is this, and at t equals infinity, that current and is this. And for the charges, at q equals 0, the charge is q initial, which is q maximum, and then at t equals infinity, the charge is 0. Now there are a couple of checkpoints here that it's worth doing to test your understanding. Now we consider a couple of examples about the application of what we have learned to some circuits. The simplest example is a charging circuit, as you can see here. So we have an electromotive force, a resistor, and a capacitor. The values are given. Electromotive force 12 volt, the capacitor has capacitance of 5 microfarad, and the resistor is 8 times 10 to the power 5 ohms. Okay, so now you close the switch, and after you close the switch, we are requested to find the RC of the circuit, and the maximum charge in the capacitor, the current in the circuit, and the charge and current as a function of time. So we start with the first thing. The RC is just a definition. Just multiply them, and as you can see, it has a value of 4 seconds. Okay, so after 4 seconds, the charge on the capacitor is 0.63 of the maximum charge, and the current in the circuit is 0.37 of the initial current. Okay, so it has dropped to 37% of its value, initial value. Q maximum is as usual, just it's C multiplied by the electromotive force of the battery, and it is this. And the initial current is E over R. That is, when there was no charge on the capacitor, it is just this. Now, write Q and T as a function of time. You just know the equation. Q maximum 1 minus E to minus T over RC. This is Q maximum that we have just found. 1 minus E to minus T over RC. This is RC, so that's how it varies with time. And for the current, it's I initial, which is 15 microamperes that we have found, E to minus T over RC, microamperes. The current is in microampere here, okay? Or if you want it in ampere, you have to multiply by 10 to minus 3 here. So this is how the charge and the current vary with time for this particular circuit with this R and this C given. Now we move to discharging a circuit where we are discharging a capacitor in this case. So there is a capacitor of capacitance C is being discharged through a resistor. Now the first thing, this is a general circuit, okay? So there, what we are going to derive here applies to any circuit. After how many time constant is the charge on the capacitor 1/4 its initial value? So after how many RCs we will have the charge equals 1/4 of its initial value. In other words, we want to have Q equals Q initial over R. Well, so we want to find T divided by RC, T in terms of in units of RC, that will make this possible. So QI over, so we need to QI e to minus TRC equals Q, we set it equals to QI over R, and we find at what T does this hold. This is the equation, okay? And to do this, well, you just cancel this out and you get, so this, so 1/4 equal to minus T over RC. You want to find, to solve for T, you have to take the ln of both sides in this case. And ln of 1 is 0, so minus ln of 4 is just minus ln 4 is equal to this. And if you solve for T in this case, you get 1.39 RC, okay? So after 1.39 RCs, the charge will drop to 1/4 of its value. Now, if we want to ask the same capacitor, it has energy stored in it. Now, as the charge, as it discharges, as it loses charge, it's also losing energy. Where does the energy go? It's dissipated in the resistor. So after how many time constant is that energy reduced to 1/4 of its value? Well, this is the expression for the energy, Q square over 2C, and you substitute for Q square, Qi e to minus T over RC, and square it. So this is Q initial square. E to minus T over RC square is become E to minus 2T over RC, and divided by 2. You want this thing to be equal to 1/4 the initial energy. The initial energy is this, because the charge is this, initial charge is this. After cancellation, you have this expression which you want to solve for T, and if you solve for T, you get about 0.7 tau. So the energy reduces to its 1/4 of its value after 0.7 RCs, 0.7 time constant. So very soon, actually. Okay. Now, a final example. This is a very constructive example. It's about the energy delivered to a resistor when a capacitor is discharging through a resistor. So we have a 5 microfarad resistor, and this is charged to a potential, so that electromotive force which has a potential of 1800 volts. Okay, so after it's fully charged, the potential difference across its terminals or its plates is 800 volts. And then you start discharging it. After you fully charge it, you start discharging it across a resistor. Now, how much energy, the question is, how much energy is delivered to the resistor in the time interval requested for the capacitor to fully discharge? In other words, when the capacitor fully discharges, it loses all the charge that is accumulated, that it already had across its plates, which means all the energy that was stored also there is lost. How much energy by that time, when this happened, how much energy has this capacitor delivered to the resistor. That's the question. Okay. Now, the starting point is to note that the capacitor plus the resistor together are an isolated system. Okay, look them at the isolated system. And the energy transfers that are happening there are not changing the total energy of the system. What energy? What is the energy of the system? It is the potential energy of the capacitor and the internal energy of the resistor, which is what? The thermal energy. So what's happening here is that potential energy, as the capacitor discharges, potential energy is lost because the charge leaves the plates, so it's losing potential energy. Where does this go? It changes into thermal energy. It increases the internal energy of the resistor. So we say that delta U, the change in the potential energy of the system, plus delta E, the change in the internal energy, should equal to 0. Why? Because there is no W external. There is no external work done. Okay? Or delta U equal minus delta E internal. That is, the drop in the potential energy, in this case it's a drop, will equal to the rise in the thermal energy of the resistor, okay? Which is heat, in this case, which will radiate outside. So delta U final minus initial, it becomes 0 after it's fully discharged, minus U initial, plus delta E internal, it is the total internal thermal internal energy of the resistor, okay, minus at the beginning, before discharging start, the resistor was at room temperature, it didn't have, and we take this as 0 internal energy, so it had it 0. So from here you get E internal equals U E, and you call E internal, you call ER. That is the energy in the dissipated in the resistor. So this is equal UE. What is UE? The initial energy stored initially in the capacitor. But we know what is this. It is 1/2 CE square, and so the energy delivered to the resistor is just the initial potential energy stored in the capacitor, which eventually it loses. So that's this. That is this is the expression for that. So this much energy is dissipated into the resistor eventually after the capacitor has fully discharged. After the capacitor has fully discharged. And if you calculate it here, it is about 1.6 joules for this particular example. We can calculate, we can evaluate this, we can calculate or derive this expression in an alternative approach. And how is that? Well, we say that the power is just dE by dt. It's a general result. And therefore, the power is DER by dt. That is the rate of change of delivery of energy to the resistor. And you can integrate this equation. So just multiply this by dt. So dE becomes p dt, and integrate it. Integrate it from where to where? From 0 to infinity. And call it ER because now I'm specifying this to the resistor. Okay? So I want to find the power in the resistor. So ER, the power in the resistor, is equal integral from 0 to infinity. The power, the energy delivered to the resistor at a power P, at a rate P, is the integral of the power from 0 to infinity. Why infinity? Because 0, because you started discharging the capacitor, and so transferring power to the resistor at 0, and the capacitor discharged after a long time, which we call it infinity. So PT. Now what is P? P is I square R in a resistor. Okay? So this is I, because this is the discharging, the current in the discharging circuit. It's not constant now, but nevertheless you can square it. And so you substitute this I here, you square it. This is Q square over R square C square E to minus 2 TRC. So when you square it here and you integrate, this is constant, you integrate this, a straightforward integral, and you get this integral and substitute the limits. And note that at infinity, you know, this thing goes to 0. then this is the expression you get, which is exactly this. What does this say is that if you integrate the power, that is the rate at which is I square R, which is a function of time now, delivered to the resistor as the capacitor discharges. If you integrate this from 0 to infinity, then you get this expression, which is for the total energy that has been, now this is energy, dissipated into the resistance as thermal energy, or the energy that, this is the change in the internal energy of the system. Okay, so this is exactly the same expression that we have found by just applying conservation of energy upon considering the circuit, the capacitor plus the resistor together as a closed system.